So welcome to today's webinar. Before passing the floor to Theodora, Antonio, we just wanted to go through a few housekeeping rules. So in this webinar, you will not be able to take the floor to ask questions. So you will need to put your questions in the chat, which you can do at any time. And your questions may be addressed periodically or during the Q&A phase toward the end. If you have any technical difficulties, which you could have connecting to this platform for the first time, especially with your audio, please try to click on the cog wheel and adjust your audio output, for example, to see if you can hear us. And then if the problem persists, you can try to join the session in a private browser. So you can try those tricks. So nothing further to say here except for thank you for joining us. And without further ado, I pass the floor to Theodora. Antonio?
Hi, everyone. Good afternoon or good morning where you are, or good evening. Welcome to our first webinar on the Copernicus Data Space Ecosystem, a pioneering platform offering comprehensive access to Earth observation, data, and services. I'm very happy as this initiative marks a significant evolution from the precursor data hubs, improving data access and processing capabilities. And today we're very happy to have Andras Zlinski. I hope I didn't butcher your name, I'm sorry. The Chief Evangelist of the Copernicus Data Space Ecosystem with us. And he's going to provide us with an in-depth overview of the platform and guide us through a very practical demonstration. So I'm sure you'll find it very, very useful. As Evan said previously, we really encourage you to actively participate in this hands-on session with your computer using the chat, etc. And we are here to answer your questions or anything at the end. Thank you very much once again, Andras, for being here, and I pass you the floor.
Thank you very much. Hello, everybody. Before we start, I would like to encourage you to register to Copernicus Data Space Ecosystem if you haven't yet. At the top right of the landing page, there's a login button, and if you click that, then the registry form opens up. It's completely free. It's only for the purpose of statistics and user quota management. So for the second half of the presentation, which is going to be a more hands-on walkthrough, you will be able to access things if you have already registered. So my name is Andras Zlinski. I'm a community evangelist, communication person for Copernicus Data Space Ecosystem. And in this talk, I would like to introduce you to, first of all, the motivation, the main features for Copernicus Data Space Ecosystem. And then after that, to really walk through the website and the functionality in a bit. So Copernicus Data Space Ecosystem is a data infrastructure, to put it in 2 words. It is mainly about data access, making data available. We all know that Earth observation satellites are orbiting the Earth and producing terabytes and terabytes of data every day, and these have to be downlinked and stored in a web server to made available over the internet to you. So far, this functionality is more or less what Copernicus Open Science Hub also did before the data space ecosystem was launched. But on top of this, the new idea is to include the processing infrastructure inside the ecosystem. So this is a simple result of a processing pipeline. This is a time-lapse animation of Stromboli volcano in Italy with a shortwave infrared visualization highlighting thermally active pixels. So such an insight is a result of a data query from a large data set, and then a processing algorithm, and finally a visualization. This can be created inside the ecosystem without downloading a single pixel, without moving data through the internet inside the ecosystem. And in addition, data visualization, so creating a graph or a map or some sort of another rendering of the quantitative information from the image, this can also be done inside the ecosystem, and the final result of this visualization is what is passed on to your computer. So all in all, Copernicus Data Space Ecosystem is a data infrastructure that takes care not only of data access, but also processing and visualization. And as you can imagine, this is massively reducing the amount of data that you have to move. So a good infrastructure is not a data infrastructure that moves a lot of data. It's an infrastructure that actually avoids moving a lot of data, and it allows you to look at only the data you are interested in. This is the approach for Copernicus Data Space Ecosystem. The reason for this is simply the volume of data. We are producing with the Sentinel satellites a volume of Earth observation data that would be impossible to handle in any other approach. So downloading all that data, storing it at the local server demands such an investment that it's just not practical anymore. But for this reason, the Commission has invested in the Copernicus Data Space Ecosystem, and now we have this infrastructure I'm going to tell you about in a bit more detail. So at the core of Copernicus Data Space Ecosystem, of course, we have the Sentinel data online repository. This is where the data is stored. This is where the data comes from and can be accessed. But instead of simply downloading the data, now we have these downloading and processing APIs, application programming interfaces. These are the tools that enable the rest of the functionality of Copernicus Data Space Ecosystem to work. So on top of these APIs, we have a data visualization and analysis and export surface, the Copernicus browser, which works in your web browser. It doesn't need you to install any software. You can look at imagery, you can export it, you can perform analysis steps, and I'll walk you through this in a couple of minutes. In addition to Sentinel data, we also have Copernicus Contributing Missions data and additional Earth observation data in the data warehouse of the ecosystem. And a lot of this data is currently in the process of being uploaded and updated. So we hope to provide a lot of complementary data to aid your analysis in addition to the Sentinel data. We have cloud computing capacity. Of course, a lot of this processing, if you want to do large-scale data analysis, has to be done in the cloud. And so the capacity has to be part of the ecosystem. This is tied to user quotas, and we can talk about that in the end. But there's also the option to actually procure virtual machines that already have the data collections on board inside Copernicus Data Space Ecosystem on a commercial basis. And in order to make all this not just feasible, but easy, we have onboard code repositories and a code lab, which provide different ways to access the data and different ways to support you when you are developing Earth observation pipelines in your code. And finally, last but not least, we have the federation approach. We expect to federate with different data spaces and provide user identity services to these data spaces to make sure that you are able to connect external data into the ecosystem from the data source of your choice. So all these components together provide a transformative solution, an open ecosystem that's open to additional data sets and additional partners, whether from the public or from industry. Of course, the first thing I want to talk to you about is data. So Copernicus Data Space Ecosystem is the official source for Sentinel data. It's the authoritative source. Anyone who's distributing Sentinel data over the internet is getting it from us. So this is the place where the data is released the fastest, the earliest, and it's definitely up to date. And it also has a digital authenticity trace. So one of the new features of Copernicus Data Space Ecosystem is this traceability API. Every image has a hash inside, which is kept as it is passed on through the pipeline. And so any Copernicus Data Space product can be checked even after processing to make sure it has not been tampered with, it has not been modified. The data is not just available, but immediately available. I know a lot of you remember the rolling archive approach of the DIASes and of Copernicus Open Science Hub, where the last 2 years were immediately available, and everything before that had to be requested from the rolling archive, and then you would wait and get a zip file for download. Now, everything is immediately available. There's no rolling archive. Currently, we have 64 petabytes, and we hope to go way beyond 100 petabytes in a couple of years. And this is actually quite a few years. So 2028, 6 years from the launch of the project, this is the continuity that's ensured by the service level agreement. So in the same way that the Copernicus program is here to stay with us for a long term, for several decades, the Copernicus Data Space Ecosystem is governed by this agreement. You can make sure that it's going to be here at least for 6 years, but we are already negotiating for extension to 10 years, depending on EU budget cycles. So just a quick overview of the satellites. We have Sentinel-2, Sentinel-3, and Sentinel-5P. These are the optical satellites we work with. Sentinel-2 is the main workhorse of vegetation and agriculture monitoring, and it also produces high resolution, really high quality true color images for you. It has a 5-day revisit time at the equator. Sentinel-3 is mainly for marine applications, and I have to tell you that in Copernicus Data Space Ecosystem, only the terrestrial and coastal data are included. The marine data have a different data space, the Ocean Virtual Lab. That's something different, also with a different approach to processing. But Sentinel-3 provides daily revisit. It has high spectral resolution, and it also includes thermal imaging with a twice daily revisit time. So this is really a powerful tool also for disaster management. And Sentinel-5P focuses on air pollution. It has spectral bands allowing you to monitor nitrogen dioxide and fine dust in the air, carbon dioxide. So this tool is this satellite is for air pollution monitoring. It has a relatively low spatial resolution, but also a daily revisit. Of course, optical bands are obstructed by clouds. We have this problem that in regularly cloudy places, optical satellites have some limitations. But we also have Sentinel-1, which is a radar satellite. So this measures in the microwave spectrum of electromagnetic radiation in C-band. It can easily transmit and receive through clouds and rain. It does not need sunlight. So in regions that are frequently affected by clouds or which have, for example, dark polar nights, this is a really, really efficient tool. It also allows, under some conditions, to see through dry sand. So it has many, many capabilities that nicely complement the capabilities of Sentinel-2. So all this data is there for immediate access, including both download and processing. And right now we are in the process of updating with Copernicus Contributing Missions datasets, including a very high resolution European coverage dataset. The Copernicus digital elevation model is already online. We are producing cloudless mosaics. Sentinel-2 is already there. Sentinel-1 is in the pipeline. And also auxiliary data and engineering data for those who want to perform their own geometric or radiometric correction. This is also available inside the data space. Just a quick look at our roadmap. We have a large set of data coming up actually in March and April. These include the very high resolution mosaics from the Urban Atlas and from the European VHR coverage. We also have monthly Sentinel-1 mosaics, so analysis ready data from Sentinel-1 coming up. And meanwhile, we are working on developing the stack access to add further metadata, and we are supporting new functionality in OpenEO and Sentinel Hub APIs. And let me dive into this in more detail in a second. So in the next step, I want to talk to you about API access. So an API is an application programming interface. It's a piece of code that allows your code to communicate with our code. It allows you to access satellite imagery pixels in the same way as you would access quantitative variables inside your code. Anybody who's done a little bit of coding has defined a constant, and then you can access this constant in mathematical operations. This constant can even be a list or a tuple or some text, or it can be a variable from a satellite image collection, which is brought to you through APIs, through application programming interfaces. This is what APIs are about. Different APIs have different outputs, different results. So we have various types of APIs that enable streamlined access to Sentinel data. The first step typically is a catalog API. Catalog APIs allow you to query the database, and it returns to you a list of data sets. It tells you what imagery is available for your time frame of interest, for your area of interest. OGC APIs from the Open Geospatial Consortium return a complete map, which can be embedded in GIS software or also in a web browser or a web GIS. So these APIs provide a complete visualized map that you can use. Processing APIs are the most frequently used workhorse. This returns a raster product. So if you want to create a visualization, or if you want to actually download an image, then the process API is going to be your weapon of choice. here you can also set the processing algorithm and the selection, and then you will have your downloaded data product. We will look into this again in the hands-on. Now, the statistical API is a very powerful tool because in most cases, you don't actually want the imagery. You want some sort of a quantitative insight from the imagery. You want a histogram. You want a time series. You want to create a database that can be passed to a machine learning engine. And this is what the statistical API does. So it actually does calculations on the pixels and returns the results of these calculations. And then we have the bring your own data APIs, which make user-generated or third-party data compatible with the online datasets. And we have the OpenEO API family, which is a completely format and language independent processing toolkit that does end-to-end processing within the same environment. So the list of catalog APIs available, OData and Stack and OpenSearch, again, are probably familiar to people who have been working with Earth observation for a long time. These are absolutely there. So we are backwards compatible with the Copernicus Open Science Hub. They allow querying and downloading the data as a list of images, and can also create a URL link, which allows you to access the data in some sort of a web-based system. But we also have the Sentinel Hub Catalog API, which is a very powerful filter. It allows you to select not only based on area, but also data quality, on pixel values, cloudiness. So this is the first step if you want to explore a data set for an area. OGC APIs, they produce services. So we have these WMS, web mapping, web coverage, web feature, and tile services, depending on what you want to integrate your data with or what you want to embed it in. You can create a complete web GIS or an online map system, which allows you to access satellite imagery directly inside the website. And one of our most powerful features, actually, you can see a small screenshot of it on the right side, is the Copernicus Data Space Ecosystem QGIS plugin. So this is a plugin that you can install on top of QGIS, and it allows you to directly visualize satellite data using the same calendar interface that you use in the browser. It really enables you to work with satellite data as a base map, or to put it in as a background, or actually to perform analysis from raster to vector conversions. The Process API delivers the image from the satellite data collections. Again, this also allows filtering, but the main functionality is called the eval script. The eval script is a combination of a pixel operation, a mathematical operation on a set of pixels, and a visualization tied to this operation. It can deliver raw band values, of course, as well, but it's mostly used to deliver spectral indices. This is KNDVI, so kernel-based NDVI on this image, and it's visualized on a palette from light to dark green, obviously. And all this is embedded in the eval script. So this means you're requesting data through the Process API. A raster is being returned to you, but this operation already contains the calculation of the spectral index. So it's not like it used to be, where you download the data by granules and bands, and then you do the spectral index in a band math calculator on your server or on your machine, and then you visualize the result in some sort of software. All of this can be done in one step, and you only get the result. The statistical API takes this to the next level. This takes an area of interest. So you need to upload a vector outline of the area where you want your statistics to be performed. In the simplest case, this is just a rectangular bounding box. And then you also have to select the steps of your time series, from daily to monthly to yearly, depending on what you're interested in, and the name of the statistics that you're interested in. It could be a histogram, it could be quantiles, it could be standard deviation. For a single area of interest, this can be very quickly calculated, even if you have a long time series where you want to assess the quantities of your pixels. If you work for a multitude of areas of interest, you can do this in batch. So it's possible to define a bucket, and the output of the statistics calculations are going to be calculated asynchronously in a very efficient way, and loaded to this bucket where you can find them afterwards. So this is how it is done operationally over very large areas. And for bring your own data, anything that's compatible with the cloud optimized GeoTIFF format can be ingested as a raster data and made compatible with these APIs. So if you want to do a process API combining NDVI, for example, with a drone image, you can ingest this drone image using the Bring Your Own Data API. And then you can use the pixels of one variable, one data set and the other to make a combination and process that also in the same very efficient way in the cloud. And finally, the OpenEO API family. This is a set of completely open code. So even the backend is open. It's released on Git. It allows you to work in an open data pipeline if that's what you, an open code pipeline if that's what you prefer. And it's agnostic of data formats and coding languages. It has its own data cube philosophy. So all the data sets are ingested into a data cube structure. And then the backend allows you to define a processing pipeline and run it from small to large scale. One possible interface is a graphical web user interface where you don't even need to create any code. You can just build the pipeline together similar to a model builder. And then once you have it running on a small example area, you can scale it up to a large area or even globally. Or you can also control it using JavaScript or R or Python. And it's really aiming to provide reproducible, transparent workflows. So this is very much of interest for the science community, but of course also for industry. It's compatible with all these libraries. So it really provides an interface that can be entered from many different directions. And it also provides output for code in all these languages. So one possible solution you can use is to build your model in the graphical interface, and then it creates the code which you can pull down and embed in your own code somewhere else. Moving forward to Copernicus Browser, one of my favorites. This is a completely new approach to visualizing satellite imagery. And now we're going to move to the browser. So if you just enter this URL, browser.dataspace.copernicus.eu, it's going to take you to Copernicus Browser. If you haven't registered that yet, this particular tool has most of the functions enabled also for anonymous users. Let me guide you through. So here we are in the Copernicus Data Space Ecosystem main page. And under Explore Data, Copernicus Browser is the first thing that pops up. So this is what the browser looks like. Just let me navigate to my favorite place. This is an image of Lake Balaton. As you see, the background is a cloud-free mosaic. It allows you to browse around. You can search for places in this search window. OpenStreetMap is in the background, so anything that's OpenStreetMap can be found. And then on the left-hand side, you have various options for looking into different data sets. The first one is a calendar window, and the big green button just gives you the latest image. And here, if you open up the calendar, you see the dates of potential images. The ones in gray are cloudy. The ones with a blue frame are accessible or usable. You can set the cloud coverage limit here. So as you can see, if I increase the threshold for cloud coverage, then more images get this blue frame. Yeah, this is a partially cloudy image. If I go back to the default value of 30%, some of the images go back to gray. And here I can find the data sets available. It's also possible to provide a time range, and then you are going to get a mosaic of data overlaid within this time range based on the highest quality or the most cloud-free pixel. But if you want data from an exact date, then you need the single dates. In this panel, you can select the data collection. Just very quickly to flick through. This is Sentinel-2, a true color image. You can also look at Sentinel-1. Here again, you can ask for the latest date. And here you will see a Sentinel-1 image. You see that this is a radar image. It's cloud-free. It shows you the structure of the vegetation, the changes in the water surface. You can look into Sentinel-3. It's a different scale of observation. low spatial resolution but very high temporal resolution. And going back to Sentinel-2 in a moment. Oh yeah, we also have Sentinel 5P. So you can see the individual air pollution indicators listed here. Sentinel 5P is heavily influenced by cloud cover. You will see that in some cases the data has gaps, but it gives you again an overview of the aerosol situation in this case. And our new favorite, here's the elevation model. Actually, this is a static data set, but it's a very nice background for interpreting what's going on in a satellite image. Our new favorite data set is the Sentinel-2 mosaic. So this one is level 3 analysis ready data. It's a mosaic created from 3 months of data with the cloudy pixels filtered based on the Sentinel-2 level 2 processor and the first quartile actually of the image pixels, so not the average, but something related to that is calculated to give you a completely seamless wide-scale overview of the situation. It's a bit noisy over water because it's taking pixels from different dates, but over land, it's a really, really capable data set. So these are the data collections. I'm moving back to Sentinel-2. And selecting the data I showed a moment ago, going back to March 2023. There is a set of visualization options available. So this is infrared false color, highlighting vegetation in red, working with the wide near infrared band. Highlight optimized natural color is a visualization that you want to use if you have a lot of dark or very bright areas. It handles the transfer functions of the colors a bit differently. NDVI is the classical green vegetation index. And we have different additional ones down here. Now, one quick option here is to add to a compare, or to add to pins, or to add to a time lapse. If you add it to a pin, it's just placing a mark for this specific location and this specific date, and then you can return to it from your pin collection if you're a registered user. For adding to compare, that's a really nice way to overlay images from different dates. So if I go back to December, hope I'm going to have the coverage. Yes. Takes a second to load. And then I add this image to the compare as well. And I move over to the compare window. And you will see that I can change the opacity. And then as I move this slider, the image morphs into the image below. So this one is from December, this one is from March, and I can compare changes as they happen. This is a very nice tool also for education or for keeping track of processes that are actively happening at this scale. So we use it a lot. Moving back to the visualizations, there's also an option for the custom visualization. So one thing you can do is just to drag the bands onto the RGB fields and create a custom visualization. And then you can test many different band combinations of your choice. Or you can create a classical differential index, again with the drag and drop interface. And you can apply a threshold to the visualization if you want. And of course, the most powerful tool is the custom script. So there's this scripting window, which allows you to use short JavaScript code snippets to input any kind of visualization and any kind of processing that you can imagine. And we actually have a custom script repository. So this repository holds way over 100 different scripts. Each of them has some sort of visualization code that you can copy. So this is the full text of the code itself. And then there's usually a short explanation of the script itself and how to use it. So this is what you can do with visualizations in the Copernicus browser. Just a couple of other tools before we move on. I just go back to NDVI. If we select an agricultural parcel and draw an outline around it, I have an area of interest, and this allows me to look at the histogram of this area on the image. So these are the NDVI values with their frequency inside this particular place. This is from Statistics API. I can also do a time series. So I can actually query a year of data, apply a quick cloud filter, and I have a time series showing me the growth of vegetation inside this agricultural parcel at my fingertips. I can even export it to a CSV for further analysis. There's also the option to download imagery. If you want to do this for further processing and analysis, then you probably want to use the search tool. This has quite detailed filters. You can select the different satellites, orbit numbers, product availability, the time frame, and then if you hit search, it's going to give you a list of the data products for this particular place and time, and you can visualize them on the image. You can also look into their metadata, so everything is here. You can even actually download individual single files based on the folder structure of the granule. So if you only want the metadata or you only want one band, you can actually pull it down from here as well. But if you don't want to download data for further analysis, you just want to download it as a visualization, then here's the download tool. You can crop it to your area of interest if you want. The basic download gives you a very small image of a couple of hundred by a couple of hundred pixels. This is what we tend to use in social media or just to share to people. An analytical download, here you can select the pixel resolution, including custom resolution. You can select the coordinate system, and you can either choose a spectral index or the actual raw bands of the image. But if you want a print quality image for your bedroom wall or a poster, then you can actually set the image quality yourself, and you can download a really high resolution image. It takes a while, but it's usually worth it. We also have tools for creating time-lapse animations. So here you set the time frame, the cloud coverage, the tile coverage, you search for images, and you get a time lapse showing you the change. And you can download this as a GIF, and again, you can embed that. You can send it to your customers or put it on your social media. But sending images around is still quite a hassle with all that data. So I think the most powerful way of sharing images is just this little link here. So if you click on this, you get a URL, and this URL is going to take anyone straight to the same location and the same image with the same parameters inside the Copernicus browser. Since it is completely free and open, you can share imagery this way with anyone you want. Moving back to the browser, there's going to be a question and answer session in the end, so I'll try and go back to follow up on the questions. I want to talk to you a bit about the onboard code lab and the code repositories. So the next thing we want to walk through is the Copernicus Data Space Ecosystem Jupyter Lab. And once more, I would like to encourage you to register. I have a different window here. The Jupyter Lab is here under Analyze Data, Jupyter Lab. It has a bit of an explanation of what this is and how it works. We have some explanatory videos. And if you click Access Jupyter Lab, then you will be prompted to clone a server, and you will have an online server of your own. So this is where you end up. You have a storage space for yourself where you can put your own notebooks. And you also have plenty of example notebooks here for OpenEO. These are typically complete end-to-end processing analysis chains that you can investigate and you can work through them. And the same goes for Sentinel Hub, and I'm going to walk you through the simplest among these, the Introduction to Sentinel Hub APIs. So this is how this works. But before we start going through the notebook, we need to open up our dashboard, our Sentinel Hub dashboard, and create an OAuth client. So again, analyze data, Sentinel Hub, and this is your user dashboard. And here under user settings, you will see your OAuth client. And the way to go when you are creating your first one is just to hit the create button here, give it a name. And now you will see the client ID and the client secret. You have to copy these locally with these copy buttons to a text file, and then you will be able to paste them into your code when the time comes. Okay, coming back to this notebook, this is a quick walkthrough of the individual Sentinel Hub APIs. The Jupyter lab allows you to work and develop Jupyter code without setting up a coding environment of your own. And it accesses the data collections straight from Copernicus Data Space Ecosystem, again, without downloading or without setting up the collections individually. So first here, we import, we have to set the kernel. Typically, it's Sentinel Hub by default, but these kernels give you a variety of Earth observation libraries that you can use for processing. You can also define your own. So we import the dependencies, we use pandas, we use getpass, we're going to use matplotlib, and these are the individual APIs from Sentinel Hub. And then we're going to handle our credentials. You will see if you are running this notebook on your side that these two lines are commented out. You have to remove the comment. And then if you run this cell, this line will also be commented out, but you want to save a configuration, so remove the hash sign. No, here we go. So it's going to look like this on your side, but we remove that and run the cell. And now it prompts me for my Sentinel Hub client ID. So this was the ID that I copied from the dashboard. I paste it in. And now we can move on to setting the area of interest. So we define this variable, the area of interest. It's a simple rectangular AOI. You can, of course, define your own. And the bbox finder is actually an easy tool to do this. And then we define a couple of further parameters. The resolution is going to be 10 meters now. This is our area of interest, including the coordinate system. And then we just print a message to show that the system has recognized these variables. So first of all, we define the catalog API request. And this is going to take the configuration that we defined up here, which is saving our credentials. So by running this cell, we now activate the Sentinel Hub catalog API. And now we are building a request. The request takes the bounding box we just defined. It takes a time interval that we can actively change here. And then it's going to iterate through the Sentinel to L2A data catalog, the collection, and it's going to return these fields from the catalog. So if we run this small request, we are getting a list of parameters. They are telling us the ID of the individual images and the corresponding date and time. This is the output of the catalog API. This is what you can use to explore the data collection. Now we move on to the process API. This is going to return a raster. And in the first step, we are going to request a true color image. So for this, we need an evaluation script, which is going to tell us what's happening with the pixel values. Then we need the data collections and the response and the bounding box. So here we define the evaluation script. It's just taking bands 2, 3, and 4 and creating an RGB image, so a tuple of the red, the green, and the blue band. Then here we have the data request itself. The eval script is going to be the one we defined above. The data collection is Sentinel-2 and L2A, defined here with the service gateway from dataspace.copernicus.eu. Here we have a custom time interval, and now we can run this request with the bounding box, the size, and the configuration that we defined in the previous steps. Okay, now we define the image as the output of this data request. So this is request through color. This is what we defined here. It takes a while because this is where it's actually collecting the image pixels. Then we check the type of the data to be sure. And in the final step here, we're going to plot the image using the matplotlib plot image function. So the image is defined up here. And we are printing the image itself. Again, it takes a bit of a while because it's moving data. So this is how you get a true color image inside your notebook. We take the same steps to have an NDVI image, but here we are defining a different eval script. So we are using the bands 4 and 8. And then we are doing this mathematical function to have the spectral index itself. And then here we are applying a set of colors. So these are the values of the red, green, and the blue channel, which is going to give us the green scale visualization that we use. And here we define then a new request where the eval script is set to NDVI. The input data is coming from the same collection, and the time interval is the same again. We define the image as the output of this request. We print out these things we wanted to check, and then we create the image in the next cell. So this is an NDVI image, and it's visualized according to the palette that we defined in the eval script here. Now we move on to statistical API. This is going to return a set of numbers where we can actually compare the NDVI time series for individual fields. We redefine the eval script because now it also includes a data mask output. If we want to do statistics, we have to separate the cloudy pixels from the regular pixels because we don't want to include the cloudy ones in the statistics. We define two areas of interest, two different fields based on these polygons. And then for the statistical API request, we have the evaluation script here. We have the time interval. And this is the interesting part, the aggregation interval. Here we set that we want to collect the data in steps of 10 days. The input data is coming from the same data collection. Actually, this is level 1 now. The geometry and the configuration are already defined. And so out comes a JSON, which actually has the statistical values min, max, mean, standard deviation, sample count, and no data count for intervals of 10 days. So 1st of May, 11th of May, 21st of May, and so on. But this is just a JSON. It's not visualized. So we pull it quickly into a pandas data frame. And then we define a small table, which is going to include the data. And then again, once we have the table, we can display it with matplotlib. This is just regular Python visualization. And here we have an NDVI time series. So don't forget that we actually crunched through 4 months of Sentinel imagery. We separated the cloudy images from the regular ones. We calculated NDVI for the area of interest. And the only thing that we actually downloaded are these statistical values that we have in this data frame. We can also do the same thing for 2 different fields if we want to compare their growth, their time series. And then here we have a comparison. So this is a very quick example of how the catalog, the process, and the statistics API work. You can do this, of course, at a much larger scale. You can crunch through a lot of imagery to investigate at the national or a continental scale, depending on what you're interested in. There are different example notebooks that are more in the direction of end-to-end processing. So this one on ice monitoring, for example, it really defines an algorithm, a threshold. It measures the area of ice, and then in the end, it gives you a time series of ice formation and melting. So feel free to explore this Jupyter Lab, and of course to define your own notebooks. Now, in the last step of this presentation, I just want to show you where to get additional information. So this is the documentation page. Documentation.dataspace.copernicus.eu. This is where you will find information on the individual data collections. This is where you will find information on the APIs, including a lot of code examples, also for OData and Stack and OpenSearch, of course. There are different applications inside the ecosystem that you can find here, where you can look for the individual support and documentation. And we also have a community forum. I would really like to encourage everyone to submit your questions or your problems to the forum, because this will allow other users to also learn from your questions and see what has concerned you. So this is a very important source of communication with our users. So just to summarize in a bit, I think that Copernicus Data Space Ecosystem is really a transformative thing. So this combination of data access, code libraries, and the API accessing tools really allow a new way of accessing data and a new way of working with Earth observation data. If you're from a government agency, you have this trusted, solid source of data that you can work with for a long time, and you don't need to invest in or procure satellite data infrastructure. For education and for science, again, these are trustworthy images. You can build reproducible pipelines, and you can teach EO coding in relatively easy incremental steps. And if you work in industry, you can prototype and scale up without heavy investment. You can build solutions. You can share the data sets with your clients through the browser without them buying expensive software. And you can join this federation, this ecosystem, to commercialize your solutions. So thank you for following this through. I already see that there are a lot of questions, and I'm going to move over to them in a moment. But really, to sum up, I think that Copernicus Data Space Ecosystem is a big boost for the Earth observation industry. Before we move over to the questions, I have an invitation for you. We are organizing the Copernicus Data Space Ecosystem user review meeting. This is a hybrid meeting. You can participate online or in person. It's on the 15th of April. It's also announced on our website. So this is an opportunity to learn more about the ecosystem, and also, of course, to share your feedback. And I think the most important question is really about the credits, the data volume that you can access. And so I'm trying to move over to this. Quotas and limitations. So the limitations are defined in terms of requests per month. And this is based on processing units. The standard set of 10,000 processing units per month, just to put this in perspective, 1 square kilometer of Sentinel-2 imagery is, I think, 6 processing units. No, the other way around. 1 processing unit is 6 square kilometers of Sentinel-2 imagery with the full bands. So, for example, if you want to create a mosaic of Austria with all the bands, you can do this 3 times a month using your general basic user quota. But if you are a European public institution, if you work, for example, for environmental monitoring, or if you're an agricultural paying agency, or another participant of European public government services, then you can apply for a Copernicus service user quota, and that has a much wider quota, essentially allowing operational national to continental scale processing, and that allows you to really work with the data in a near unlimited way. I quickly answered the publication of the images. So every image that you download from the Copernicus Data Space Ecosystem is free to publish. You have to credit the Copernicus program and the Sentinel satellites, but the Sentinel data is completely open to use for practically any purpose whatsoever. I see a question about federation and user services. At the moment, we are federated with CREODIAS. CREODIAS is essentially providing the commercial services on top of Copernicus Data Space Ecosystem. We are partnering also with Mundi, which is a web service and data service provider. And we also have Sen4Cap as a sort of software as a service or platform as a service solution inside Copernicus Data Space Ecosystem. Oh yeah, and this is the place to apply for the custom offering for this Copernicus service account for paying agencies and other public agencies. I see a question about links with other common European data spaces. Well, we are closely linked to the Copernicus Land Monitoring Services and the Copernicus Data Store. We are actually working on embedding the data sets directly. So you will see that Spot and Proba are accessible as data collections. We also have SMOS, MVSAT, actually Landsat, and the Copernicus Services accessible as data collections. These are not all accessible in the Sentinel Hub APIs in the browser yet, but you can query them and you can build solutions on top of these data already. We are working on federation. So the vision of the system is really to federate with other European data spaces, for example, the European Open Science Cloud or the European Green Deal data space. We're negotiating with these partners to find the best solutions because these have to be sort of tailored to the data types and the needs of the users. Atmospheric collections, yes, that's an easy one, at least for Sentinel-2. Just looking into the browser. So in the Copernicus browser, you can simply select between level 1 and level 2. And then level 2 already contains the atmospheric correction for you. But it's also possible to apply your own atmospheric correction or to use different correction systems such as Force, which have a software image in the commercial branch of Copernicus Data Space, which is CREODIAS. I'm not aware, unfortunately. Oh yeah, Simple. It's generally the whole idea to open data and to make it easily accessible, which is the background of many of these European data strategies, is of course the driving force also behind Copernicus Data Space Ecosystem. But I am not aware of any additional standards or any further activity in harmonizing these. Is there a question I have missed earlier?
There was one question way up about NDVI values between Copernicus browser data and L2A products. It's back at the beginning. It's yeah.
I don't see that. For some reason, I can only open the live discussion and not the questions panel. You can just, can you read
I can read it to you. So it's R2 Kivimaki who says that we were doing pixel-based comparisons of NDVI values between Copernicus browser data and L2A products downloaded to a local PC from which the NDVI was calculated. And the NDVI values of daily time points between browser time series and locally produced time series differed with up to 0.2, I guess, of difference, which is quite a lot for an index like NDVI.
Yeah. I can't answer that, unfortunately. I suggest you post it in the forum. I'm sure my colleagues will jump on this because this is really of interest, but I don't know why this is. I'm thinking about credits. There was one further about the annual mosaic. Yes, there actually is an annual mosaic. It's available under the mosaics here. So the world cover annual cloudless mosaics have been prepared in the framework of the World Cover project. These are annual. So this means that even in really cloudy places like Ireland or Sumatra, this mosaic still has meaningful data. And it's also seamless. It has a bit of a different way of calculating the data means, but this is also available. And it's not just available in the browser, it's also available as a data collection. It's just listed under complementary data, I think. Yes, here we go. World Cover Annual Cloudless Mosaics. Yes, ESA third-party mission data is also becoming available. It's on our timeline. Depending on the individual missions, of course, there's a bit of technical things to handle, so it's not coming in the next months, but it's going to be available. So the plan is definitely to use the ecosystem to share all the data that's distributed by ESA. And this actually also includes upcoming Sentinel expansion missions. Yes, the mosaic is available as a WMS. You can take the data collection ID and you can create a WMS using the OGCI APIs. There's actually quite a detailed description of the OGC API among our blog posts now.
I see there are no more questions, apparently. So I think we can conclude within the originally scheduled time frame. Thank you so much, Andras. And before Theodora gives her concluding words, I want to thank all of you for participating. You in particular, Andras, of course, very informative. As I was saying,
thank you for your interest. Thank you for being here.
When we were getting ready for this webinar, I was saying I'm a guy who lived through the time where you were receiving a couple of satellite images on a huge, very large magnetic tape. So I measure the distance that has been done since then. I also measure the distance between the time where you needed a high bandwidth, very, very powerful computer with a very big hard disk to deal with, for instance, Sentinel-1 data and the very large tiles. So this is really coming as a revolution. For those who are not familiar completely with Copernicus, I'd like to point out, in the sake of fairness and equality, that there's another access platform which is funded by the European Commission. It's called WIKEO. We will at some point also present it after they roll out their latest version, which should come in the near future. So keep posted for this. But once again, thank you for being there. Remember to, if you've got any questions that are not directly on the CDSE, you can send them to the EU Space Support Office, to my colleagues. I think we can put the address on the screen. Any question related to Copernicus, but not only, also to Galileo, also to the future IRIS-2 constellation, questions on space traffic management, etc. Write to support@euspace-program.eu. I don't see the slide. I hope you see it. Without further ado, Theodora, we're right spark on time. It's 18:29 CET. The floor is yours.
Thank you very much, Stefan. Thank you for your active participation in today's webinar, your questions. A big thank you to Andras, of course, for being here. We hope you found the session informative and engaging. I'm sure you did. So the recording of this webinar will be available in the EUSpace YouTube channel for those who want to rewatch it. For updates on the next webinars and more information, please follow the Copernicus EU on Twitter. And as Stefan said, should you have any questions about the platform, feel free to reach out to us at support@euspace-program.eu. Thank you once again for joining us today, and we look forward to seeing you in our future events.
Goodbye.
Goodbye.
Thank you, everyone. Goodbye.
Bye.